Thanks for the introduction. I'll talk about high dynamic range imagers for automotive. I'll talk about how OmniVision gets involved in HDR over the years, introduce HDR terminologies and technologies, and then I will announce our TSL technology that we're introducing today. In 2007, OmniVision introduced the first split cell pixel in automotive, 6 micron FSI. We shrunk that to 4.2 micron, and in 2014, we made the first automotive BSI split pixel, delivering 120 dB of dynamic range and LED flicker mitigation. We went on and we introduced the first generation dual conversion gain technology for automotive and deep well. Improved that in 2018, and then combined it with our third generation split pixel in 2021 on the OX03F, delivering 140 dB dynamic range and LED flicker mitigation. In the meantime, we've been introducing high dynamic range in mobile, and today I'm here to announce our first TSL pixel, a 2.1 micron automotive HDR technology. So why do we need to talk about HDR and LED flicker mitigation? Sensors that do not support high dynamic range force you to make a choice. You will, in this particular picture, you'll be able to either see outside the tunnel and inside will be black, or you'll see properly inside and outside will be completely saturated. If you don't pay attention to LED flicker, sometimes LED signs will show up clearly and sometimes they'll be half gone, which is obviously not safe in traffic. So how do we do high dynamic range? Most high dynamic range techniques come down to you take images with different responsivities. So we start with a high responsive image capture to capture the low lights. And then we start adding lower responsive images, captures, until we've captured what we want. Then we digitally gain up those lower response images to a linear response and reconstruct a proper image. But there's a price you pay. And depending on the technology you use for high dynamic range, these issues you run into may be different. But there's a few things that most of these have in common. First, you're going to burn more power. You're taking multiple captures of the same scene, so obviously that takes something. You also have to process these images and the pixel data that comes with it. The more fundamental issue is the knee point SNR. So what's going on here? As you get more light, the SNR will increase because the relative contribution of the shot noise to the signal becomes less. But when your signal saturates, you have to jump to another capture. And either you capture fewer photons to reduce the responsivity, or you have to change the conversion gain to change how electrons get translated to a voltage. And so either you'll get more shot noise or you'll get more read noise, and the SNR will drop. This is an important concept to keep in mind. This is going to come back. So we're taking multiple captures with different responses, and when you change from one capture to the other, the SNR will drop. So what are the different HDR technologies? As I mentioned, we can either reduce the number of photons we capture or change the conversion. In this first category, we can change the exposure time, quite trivial. You have long exposure times for the dark parts of the image, and then you start to reduce it to capture the highlights of the image. This, as everybody realizes, leads to motion artifacts, but it also affects how we capture LED flicker. So I'll come to that. The other way is to change the responsivity of pixels across the space in the array. This leads to a, albeit sometimes more theoretical, loss of resolution, but it most definitely hurts your low light performance, especially for smaller pixel sizes. Now we'll talk about this third category later. Let's understand why LED flicker is important. So if you have short exposures, so you don't saturate, you may not capture the LEDs when they're on. So why is this? LEDs in traffic lights, tail lights, billboards and whatnot are modulated at a frequency that is fast enough so the human eye won't detect it, but the frequency is not standardized. We can't lock onto it, and so every sensor will have a different frequency. So when the LED is turning on, sometimes you may catch it, sometimes you may not. And then you will not accurately capture the traffic sign. Again, not safe. The way to avoid this is to have a sufficiently long exposure time such that you always cover the LED on cycle. But now we've got a long exposure. It's going to saturate. So we need to find a way to make sure this single long exposure does not saturate. So what options do we have? The first option is the split photodiode. As mentioned, introduced by OmniVision in 2007, we use a large photodiode to capture the low lights of the scene, and a small photodiode capturing or stealing at best 10% of the photons from the large photodiode to capture the highlights in the scene. On top of this, OmniVision introduced a neutral density filter technology to further attenuate the signal going into the photodiode, this small photodiode, to further extend the dynamic range. And so, at least at a 3 micron node, this delivers excellent image performance. Let's look at just how good this works. So, with the OX03F split photodiode, we're combining DCG, so a high and low conversion gain read, with a capture of the small photodiode, delivering more than 100 dB of dynamic range in a single exposure, and 140 dB in total. Because the SPD, as well as the short exposure, reduce the number of photons to reduce responsivity, the SNR drop is determined by shot noise. This is not very sensitive to temperature, so the SNR drop you see will be very consistent over temperature. And as the previous speaker mentioned, you will have QE differences between the large and the small photodiode. And yes, indeed, this will require additional processing. So we have a spectral transformation engine, doesn't take up too much die area, and this does the trick. It does it so good that if I would just show you like that charge on the large and the small photodiode, it would just look like the same image. So let me show you this AB graph here. So you can see from the coordinates that the SPD and LPD coordinates are very close together. They cluster together for any white balance in the scene, and that's important because machine vision systems do not perform any auto white balance. And this is true for all of the colors you will encounter in traffic, as is shown here, and in fact, just for any colors. So again, excellent choice, 3 micron, this is the way to go. But now we're trying to shrink the pixel to 2.1 micron and hopefully beyond. So now we run into some more challenges. This small photodiode, taking up about 10% of the photons from the large photodiode, becomes a luxury you can't afford anymore at the smaller sizes. 3 micron, not a problem. Smaller, questionable. On top of that, we get more crosstalk. So why is that? We have this large red photodiode sitting right next to this tiny little green photodiode, and on the border between these two is kind of no man's land. And the smaller the pixel gets, the bigger a relative portion of the total pixel area gets taken up by this no man's land, where photons or photoelectrons may get confused and they end up in the wrong colored pixel. That leads to errors in color. As you can see in the picture on the right, the small photodiode color is a little off. Also, this small photodiode is small and smaller in the smaller pixel. So the SNR, it can deliver degrades, as you can also see from this picture. Okay, so if we want to go to ever smaller pixels, maybe the split photodiode is not the best option. So what else do we have at our disposal? There's a dual conversion gain, which we introduced in 2016, where we capture a high and a low conversion gain image at the same time. But the dynamic range extension we get here is always going to be limited by the photodiode. So low-fic is the way to overcome this. It suffers a little bit from increased knee point SNR, so that's something that we'll need to address. So combining this with our OmniVision engineering excellence, and this is a key part, is what we call TSL. So let's look at how this works. We have first a dual conversion gain capture. So we'll read both a high conversion gain, transferring the charge to the floating diffusion at very low noise but early saturation, and the low conversion gain, which would normally saturate the floating diffusion, at which point we connect the low conversion gain and we can read out. So that's step one, limited by the photodiode, as I mentioned. So this is where LOFIC comes in. When the photodiode's full, the first thing that will happen is the photodiode will overflow charges into the floating diffusion. So we're essentially integrating there instead of on the photodiode. And now we add an additional container that can hold 100 times more charge than the floating diffusion. So once the floating diffusion is filled up, which will happen very quickly after the photodiode saturates, we start transferring charge into this huge bucket. And now we can proceed and read this out. Okay, so now what do we have? We can capture the highlights of the scene without saturating with a single long exposure, long enough such that we can capture all of the flickering LEDs, and we do all this in just a single photodiode. So what does that buy us? We got extended single exposure flicker-free dynamic range, excellent performance in low light, accurate colors, and this is where TSL really sets itself apart from everybody else. We get uncompromised SNR up to 125 degrees centigrade. On top of this, TSL is the perfect candidate to scale even further. Better performance in low light. Why? We get higher responsivity because there's no signal lost to the small photodiode, right? So those 10% of photons that we would have to give up normally, not there anymore. We can also further optimize the optical stack just for the single photodiode, and we can optimize the dark current just for that one diode. So the difference in image quality is telling, at least on this display, kind of. But unfortunately, we're not as good as a state-of-the-art 3-micron split pixel. The previous speaker showed some images potentially of an older 3-micron split pixel. This is today. It would not be fair to expect our engineers to beat a bigger pixel. But what we did manage to do, if we would just scale the 3-micron performance, this is what we got. So the SNR1 is higher, which is worse. So, okay. But what we see is that the gap starts to narrow as we go to higher temperatures. So what's going on there? As the temperature increases, dark current picks up. And at some point, the entire SNR will be dominated by dark current. And so at that point, the two pixel sizes do indeed start to converge. With some fantasy, I guess we could say there's a crossover there at 115C. Now in practice, if you have a sensor with the same optical format, but more pixels, smaller pixels, the temperature will be higher, so this point may not really occur. But that's a good subject for another talk at AutoSens. We got more accurate colors. There is no crosstalk to the small photodiode because there is no small photodiode, and there is no QE differences because the DCG and LOFIC both originate from the same photodiode. We also get better SNR because, as opposed to the split photodiode, LOFIC still captures all the photon. We just change the conversion. And so we get much better shot noise limited SNR. So at room temperature, this is what you'll get. But it's not all rose and sunshine. So there is a challenge with LOFIC. As I mentioned, we are effectively integrating our photo charges on the floating diffusion and the low-fic node. These are nodes with a much higher leakage than the photodiode, and that leakage will be different from pixel to pixel and cannot be distinguished from the actual photocurrent. So this leads to an effect that we call dark signal non-uniformity on the low-fic channel. And at low temperatures, this is pretty well behaved. You get a nice narrow distribution. It's not going to bother you. It's better than the shot noise. But as the temperature increases, this gets worse and worse and worse until it gets really bad. And since this DSNU negatively affects the knee point SNR, along with the photodiode full well, what you will see again is this SNR drop. And this can be quite severe. This is a bit exaggerated for dramatic effect here. The way to improve this is you either have to drastically reduce the DSNU, increase the photodiode full well, or both. And that is what our engineers did, and pretty well. So what are we achieving? We do 4 captures with TSL. First, the dual conversion gain, then a low fic, getting us to more than 110 dB of a single exposure dynamic range. And then we add a short exposure to get to 140 dB in total. And those who glance the graph really quickly have noticed we get a knee point SNR of 26 dB at 22 milliseconds. You've seen graphs like these from our competitors. They will either report this at 11 milliseconds or at 105 or 115 C. So this is 2 times better. We'll come back to that in a second. We do all this at a single mode for all the temperatures. So there is no, you have to prioritize dynamic range, sir, or if you want good SNR, please do this, but compromise that. We just quickly look at what we get at 11 milliseconds. We get 30 dB of SNR. Now, one of the previous speakers showed the difference between 30 dB and 25 dB in an image. So here you go. And it's not just the model, we measured this. All right, so we took this pixel, we put it in an 8 megapixel sensor. We got a photodiode full well of 14,000 electrons, low fic full well, 650,000. The best sensitivity in the industry, a 0.6 electron read noise, 0.6% PRNU, 113 dB of single exposure dynamic range, and 139 in total. Low fic knee point SNR at 125C, 30 dB at 11 milliseconds. But this also means that I can actually increase the exposure time now. So when it's dark and it's warm and you want to increase the exposure time, our competitors can't do that without compromising the SNR and drop below the overall accepted spec of 26 dB on this transition. We can just double the exposure time. So this is what you get at 11 milliseconds. And this is what we can get at 22. I mean, it's not even a comparison. All right, so what's next? We're going to introduce this into a complete family of automotive sensors, different resolutions, all using the same TSL pixel. And then we're going to introduce TSL in other applications. And beyond that, only your creativity can hold us back. Here's a little movie that our marketing communications team created. I also want to thank Mike for setting up all the demos and getting this stuff to the IT guys here. And Kim for locally managing our markup. Thank you. This takes about 2 minutes. So here you can see the better SNR at the roof of the tunnel. Same story. And that's it. I'll take questions now.
Yes, please. There is the microphone.
Hello, Mariusz Madzie, SNR. So, if I understood correctly, the flicker-free dynamic range is 110 dB. It is it's not just LFM, it is flicker-free.
The flicker-free dynamic range is 113 dB.
Okay, thank you.
Okay, other questions?
Could you comment on the future roadmap going forward from this point?
Sure, let's sign an NDA.
Over there.
Thanks very much for that very interesting talk. I'm just wondering, in the architecture that you have there, like I'm seeing this reliance on some overflow and the like. I'm just wondering, what does that do to your read noise when you're basically trying to do a full reset and you're trying to get rid of all those electrons? Does it not give you much more read noise, effectively?
No, it does not, because you use this signal you've overflowed to as the reference before you transfer the charge from the photodiode. So you still get the perfect difference between your floating diffusion level before transfer and after.
Very good, thanks.
Okay. Maybe one final question? I was just wondering myself how it sense that it still make to combine this with also temporal processing at different integration times.
Well, we do that, right? So we have an additional short exposure to bring the dynamic range to 140 dB. Ideally, you may want to be able to cover that with single exposure dynamic range. That might be on our roadmap, but...
Okay, so let's thank the speaker again.